Today we're going to dive into one of the most complicated parts of the stepper dyno, and that is how a little stepper driver like this can control a stepper motor like this. If we think about timescales on a 3D printer controller or measurements, a lot of the things we know in our day-to-day basis are based on timescales of maybe half a second or a few seconds, and those things are really easy to read with a multimeter. But for a stepper motor, things change thousands of times per second. And in order to capture that, we can't use a multimeter, we have to use an oscilloscope. So today I'm going to look at the different signals coming out of a stepper driver and try to capture those with an oscilloscope so we can talk through how a stepper driver actually drives a stepper motor and causes it to rotate to the precise placements we need for 3D printing. My hope is by the end of this video, stepper drivers and motors won't be this black box where you input voltage in a step signal and get out speed, but you'll actually be able to understand the nuance and challenges that stepper drivers have to overcome in order to generate the positional accuracy, velocity, and acceleration we need for 3D printers. For starters, we're going to ask one question. Have you ever wondered why a stepper motor has 4 wires coming out of it? And what do they do? To answer that question, we're going to jump over to a diagram that shows the different wires coming into the stepper motor and how they are related to the rotor itself. So this is black, green, red, and blue. Each stepper motor manufacturer has its own color sequence, so be sure to look at this in the stepper motor diagram to make sure you have the correct wires connected to the outputs in your stepper driver. But this essentially shows the windings that are around the rotor that rotates, and that shows that there's 2 sets of windings. We'll call this phase 1 or phase A, and this is phase B. And so as you drive, apply voltage across these windings, a current is induced, and current creates a magnetic field that drives torque. So that's really the critical piece here. We want to measure what the current through the winding is so that we can calculate how much torque the rotor is having applied to it, because that affects how fast acceleration we can drive and things like that. So first off, to measure current, we need to have a device called a current clamp. And for that, I have purchased a current clamp. This essentially measures current at a really high rate, high sample rate. I believe it's maybe 80 kilohertz, something like that, 800 kilohertz. And that'll more than resolve all the current changes in the winding. The second piece is these 2 devices here, and this is just a differential voltage probe. And what a differential voltage probe does is it lets you measure positive or negative voltages across the winding. And the reason this is important is because with a bipolar stepper motor, which is what we're looking at here, voltage can be applied on either side. So ground or say 48 volts could be applied at A or C, and so we need to be able to look at positive and negative voltages in this reference frame. So here we have the picture, the output of the oscilloscope, and I have the voltage and current sensors hooked up. Over here we have the voltage connected, and the current is this kind of pink or fuchsia color. And you'll see here in a moment, we're going to capture the entire waveform of one full mechanical rotation of the stepper motor. And you'll see here, if we pause for a second, you'll see that there's a ton of stuff going on here. The voltage looks like it's jumping all over the place, and the current seems like it's going positive and negative and positive and negative. And if you could see the scale of this, you would notice that this is around 1 amp here, and this is around negative 1 amp here. So we're getting positive and negative currents flowing through this winding. What's interesting though is if you counted each of these little dots along here, you would be able to count and see that there's 50 of them. And that is a very specific number because of how full steps are correlated with a mechanical revolution of a stepper motor. And if we want to look at some equations quickly, first off, we know that 360 degrees equals 1 revolution of a stepper motor, of any motor. It's a full circle. And then in this case, we're looking at a 1.8 degree stepper motor, which means that 1.8 degrees is 1 full step of the motor. If you divide 360 divided by 1.8, you get 200 full steps per revolution of the stepper motor. And with full steps, there's something kind of like an electrical cycle. Well, you're turning on and off the different coils in sequence, and it turns out that 4 full steps is 1 electrical cycle. And so we look at full steps, 200 full steps divided by 4, and we get 50 electrical cycles for 1 physical revolution, which is why that previous plot cycled on and off 50 times. If we look at that from a purely a high-level standpoint again, you can say that 1 positive and negative sequence is 1 cycle, and so 50 cycles is 1 revolution. So if we, for the purposes of this discussion though, we don't really want to look at mechanical revolutions, we want to look at that electrical cycle. So we're going to zoom in here and look at just this single cycle. And here, at time 0, the current increases to a fixed value and stays constant for about half of the electrical cycle. And this would be steps 1, 2, 3, and 4. So this is just one phase of the 2 phases. So the other phase will be doing something complementary. But you can see here also that the voltage is turning on and off in order to maintain that fixed current throughout the entire plot. So to get a better idea of what's going on with the previous plot, which is really kind of confusing, let's translate that electrical current signal into a rotor angle of deflection. So let's say that we can basically say that this rotor has a certain angle that it's aligned to, and that is, say, a north point on a magnet. If we apply a current through either of these phases, it's going to generate a magnetic field that makes the rotor want to align with that field. So if we apply a current from C to A, that's going to align the magnetic field vertically, so the rotor is going to want to turn around so it aligns with the current. Similarly, if we turn off this one and turn on this one, the rotor is going to want to rotate around 90 degrees to continue to follow this changing magnetic field. If we continue this process for a little bit, we can see that we have a full rotation here. And this is a full electrical cycle, but not a full mechanical cycle. Again, as we just mentioned before, 50 of these electrical cycles will equal 1 mechanical rotation for a 1.8 degree stepper motor. In reality, this is a little bit simplified because there is at any one time just one phase being activated. And so the time when you're switching from one to the other, that would be a dead time with 0 torque, so we don't want to do that. So what really happens is that we have 2 phases active at any one time. And so the vector from C to A plus the vector of D to B means that we can go over this way plus this way, and we get a 45-degree angle, the sum of both of these directions and magnitudes. Similarly, we can keep this magnetic field active, and we can switch this one, and that will move the magnetic field over into this angle because this positive vector plus the vector over to the right equals this 45-degree angle. And we can keep on switching one phase at a time in order to drive the magnetic field in rotation. And so in this way, we're never losing torque. We're always having some torque or some magnetic field applied. So this is what's happening in the test we just did, where both phases are on or off in a positive or negative direction. There is never a 0 point. So I've made another simulator here, and this is going to take a little bit of explaining, but it's the same thing as we just saw before, except we have both phases when they're current, either positive or negative, shown here. So for each full step, 0, 1, 2, 3, 4, for steps 1 and 2, phase A will be positive, and then 2 and 3 will be negative. Similarly, they alternate in opposite kind of phases. And that drives this vector. So the green and yellow or orange correspond to the magnitude of these currents. The blue responds to this the angle, the sum of those two. And then the red is outputting essentially where the vector was at every point in space. So this is rotating around like that rotor did. And then this will show the electrical angle from 0 to 360 degrees for each of those full steps. We're kind of choppy here. Instead of a smooth operation, it's going to change abruptly and have kind of a step, like a stepper motor. However, this isn't really ideal because it's choppy, it's loud, and it can actually have certain resonance issues that cause speed or torque limitations. So that is how we started doing microstepping. And microstepping, what it does is it starts adding multiple steps per full step. So here, while we have 4 full steps, we're actually going to have 8 changes. 1, 2, 3, 4, 5, 6, 7, and 8. Similarly, here with phase B current is going to change as well. And this allows us to smooth out the steps so each angle between each step, microstep, is going to be smaller. So instead of about a 45 degree or 90 degree step, now it's 45 degrees. So that's better. Improved performance, reduced noise. However, as you know, most of the time we even go higher than this. So 4 full steps would be even better. Again, 4 steps or 4 microsteps per full step. This is looking better, and you'll notice that this vector, this outline here, is starting to look like a circle. And then if you start looking at the phase currents, this actually starts looking like a sine wave, and this looks like a cosine wave. And let's keep on increasing the microsteps here, and it keeps getting more and more like those approximations. 16 is very common. Again, fairly small increments for each electrical angle, and these are almost perfect sine waves and cosine waves here, and this is almost a perfect circle now. Finally, let's look at 128 microsteps, and in this case it's almost indistinguishable for phase A and B current versus a sine wave. Our increments are so small that you can't really tell that it's not a perfect sine wave. The other thing that's really important here is the vector, a circle here. This red line is almost a perfect circle. And the reason that's important is because if the radius here, the length of the blue line wasn't constant, that would mean we'd have torque ripple or varied torque throughout the different positions around the stepper motor. In this case, at least in the theoretical model, if our A and B currents are a perfect sine and cosine wave, the length of the radius will be constant for the entire circle. So the stepper motor will rotate and it will have a constant torque applied to it, which is perfect. So exactly what we want. So if we go back to the actual current plots, again, this is just one of the 2 phases. So it's this one will be simulating that sine wave essentially, where we are positive, and then we're going to come back down and be negative down here. So this would be 1 microstepping, so positive or negative. Microstepping 2 starts looking like a sine wave, and you have those 1, 2, 3, 4, 5, 6, 7, 8. So 8 divided by 4 is 2 for 2 microstepping. 4, 8, 16, 32, 64, and 128. And you'll notice as you go above about 16 microstepping, the change between 32 and 64 and 128 from how the current is actually output is very low. There's almost no difference. However, from a noise perspective, it can be improved. So this is really what we're talking about with microstepping, is we're not actually making things to have less torque or something like that. We're just better approximating a perfect sine wave. Think of it like an integration where you're looking at the delta x term. As delta x goes to 0, then you approximate the sine wave. We're just getting better and better approximations. So now, how does this vary with speed? And so for this, I'm going to be using 24 volts and 16 microsteps and the same 1 amp of current, and we're going to increase in 100 millimeters per second. So the thing to note with this scale here on the bottom is I'm going to adjust the scale here so that we're always capturing 1 full electrical cycle in the plot. So even though it doesn't look like the x-axis is changing, you'll note here that it is actually. It's going to get shorter and shorter. So here again, the voltage is turning on and off. We're getting this nice, beautiful sine wave. A little bit of choppiness from the microstepping, but not a lot. As we go to 200 millimeters per second, you'll notice that the voltage here is starting to be more positive and less negative here. We'll get to what that means in a bit. 300, we're struggling a little bit to hit those current targets we're running more and more at the higher voltages continuously to try to hit the current target. And again, this is due to back EMF of the stepper motor, which reduces the effective voltage that we can generate current. And as we keep going higher and higher, we start changing from a sine wave to more of this like weird kind of triangle shaped wave. And this means that we're not really getting a as smooth of a output in that magnetic field. If we looked at the actual vector of the direction of this, it wouldn't line up perfectly with that circle anymore. It would be distorted. And as we keep going up and up, we start having more and more issues here where not only is the shape of the wave distorted, but we actually start getting less and less peak amps. And so in this case, with the RMS of 1.02 amps, we should be getting around 1.4, 1.5 peak amps. But in this case, we're actually down to 0.9 amps peak, which means that the torque output is reduced. Remember, current equals torque in this case. So reduced peak current is reduced torque. And then once we get to around 100 millimeters per second, the stepper driver is trying its best to keep driving additional current, but we're getting nowhere near that sine wave peak we're aiming for. And this is the part where you're probably going to skip steps and things like that because your 3D printer needs more torque than the stepper motor is able to provide. And so this is where we get to input voltage, because with this diagram we're actually peaked out. With this 24 volts, we really can't go higher than 100 millimeters per second because our torque output, because of our current, is so low. So with input voltage, though, we can vary input voltage in order to increase speed. And so this can only be done if you have stepper motor or stepper drivers that can handle the increased voltages. So don't do this with a TMC 2209, for instance, because they can't go above around 24 volts. But the higher voltage 5160s can go substantially higher. So at 24 volts, again, I've changed the scale on this axis to be able to capture the higher voltages for later plots. But we're tapped out here, maybe 0.7 amps peak at 1,000 millimeters per second. If we increase to 36 volts, that's a huge shift. We're actually almost able to get up to that 1.4, maybe it's a 1.2 amp peak. It still looks like a triangle wave here, but it's, this would be very sustainable. You can probably go a good bit faster than 1,000 millimeters per second. Then if you go to 48 volts, this is actually looking pretty reasonable. We're hitting our full peak torque around 1.4 amps. And this, while it's not a perfect sine wave, it looks fairly good. And this is exciting. This means that we have a lot of overhead. At 48 volts, we can go much faster than 1,000 millimeters per second. And actually, for this motor at these settings, the max speed is around 1,700 millimeters per second with my stepper dyno and the load I have applied to it. So up until now, we've been looking at the current and how much torque the stepper motor is outputting. However, the stepper driver doesn't really care about current. It's trying to hit a current by controlling voltage. And so how does it actually control voltage in order to hit those targets? This is what we're going to get into next. So if we look at this diagram from the TMC 5160 datasheet, you can see that there's kind of three different phases that the stepper driver can have. Each of these little switches refers to the MOSFETs that can be controlled on or off to drive current through the stepper motor, which is represented by this coil here. And so we have positive voltage and ground. And in this picture, we're driving 48 volts through the coil, through the stepper motor phase, and it's traveling to ground. And in this case, the direction of the coil current right now is the same as the voltage applied to it. So the voltage is going to drive more current through the coil or through the stepper phase than it currently has. So that's like pressing the gas pedal. The fast decay phase here is opposite of that. The current through the coil is flowing this way, but if you notice, the switches have flipped, so now voltage is being applied opposite the flow of current. So this is essentially like applying the brake to your car. And then this slow decay phase is a little bit different, where both phases of the stepper motor are grounded. So there can still be current flowing through this process here, but it's not going to accelerate very fast. It's not going to accelerate at all, but it's not going to slow down fast. So this is kind of like coasting on your car. You're not applying brake to slow down, but you're going to slow down slowly. And if we look at this plot, the 48 volts at 1,000 millimeters per second, I've chopped off the second half so we can zoom in here a little bit more. And you'll see that we have these different phases. So this first one, the voltage being applied is the same magnitude, as positive, as the current. So this is increasing the current flowing through the stepper motor. Next we have a slow decay, so the voltage across the winding is 0, and the current is decreasing, but it's not decreasing super fast, but it is decreasing. And then finally we have this fast decay, where the voltage being applied is the opposite sign as the current. So the current is positive and the voltage is negative. And you can see during this phase here, the current drops off quite quickly. And then we have a second slow decay phase here, where the voltage applied is 0, both phases are grounded, and that current drops off a little bit slower, before we go back to an on phase and turn on the voltage again. And so this process helps the stepper driver control how it approximates the sine wave. There's one other really interesting part down here though, and this is where we transition from a positive voltage or positive current to a negative current. And in this place here, I believe all the MOSFETs are actually open, and so the current flowing through the stepper motor is 0 because it can't actually go anywhere. But the stepper motor is actually applying a voltage to the system, which is the back EMF voltage. Because the stepper driver can't actually control to negative 20 volts exactly at this time scale, it can only control to positive 48 volts, negative 48 volts, or 0 volts. So that's a little bit interesting here. We can kind of get a little artifact there of the back EMF. So as we go further, this is another sheet, information from the data sheet, and it talks about spread cycle and how they have this sequence of a on cycle, a slow decay phase, the fast decay phase, a slow decay phase, and then this process repeats. So this is gas pedal, coasting, braking, coasting, and then gas pedal again. So this process will repeat over and over again, and it'll decide when to turn on or decay or brake depending on these hysteresis levels that are all configurable in the driver settings. And this target current here isn't the target current of the like your RMS setting. This is the target current based on that sine wave for the given microstep and the given time frame, what current is being targeted. And we can see here, back to that same plot again, we have these different sequences here. So on, coasting, brake, coasting, gas pedal, coasting, brake, coasting. And this process repeats over and over again. So this is essentially how we can tune how the driver or how that sine wave behaves. And then during this intermediate phase, I haven't looked into this data set or the data sheet for this explanation yet, but again, that's during that transition phase from a positive current to a negative current. If you've stuck around this far, congratulations. We've basically taken a journey from how the stepper driver outputs voltage to control the current through the different windings, which affects how those different windings, the magnetic field inside a stepper motor is generated, and that affects the position of the rotor inside the stepper motor. And that controls how fast and where your 3D printer works. There's a lot of pieces in that different sequence of exactly how something is accurate, how fast you can go, how much acceleration you can drive, if there's any ripple or artifacts on your printer based on ringing or other things like that. There's a lot of pieces that we can dive into, but I really wanted to put this guide together to kind of give a primer, because a lot of the other topics will get really in depth, and if we didn't have this kind of foundation or groundwork of what is actually going on, it would be difficult. It'd be like, hey, here's a bunch of plots, but no context for actually what's going on. So I hope you have a little bit better idea of how the stepper driver actually controls phases, and I hope I can get another video out here in the future. Have a great one.